and Laurent are well known in the CP community and also outside of your community. They are authors of a huge number of papers on constraint programming and of some famous books. Nowadays, Pascal is the leader of an optimization research group at MICTA, and Laurent is professor at the University of Connecticut. Pascal played a key role in the design and the implementation of CHIP, one of the very first constraint systems which was designed at UCRC in Germany in the late 18th. During the last 20 years, Pascal and Laurent developed some major constraint system and solver. I name Numerica, a very efficient constraint solver for nonlinear constraints. OPL, an innovative modeling and programming language for optimization problems. Comet, a hybrid system which combines local search, constraint programming, integer programming, and linear programming. All of these systems had a strong impact on CP. So I think everyone here is eager to know what is inside Objective-CP, and I give you the floor for 1 hour.
So thank you, Michel, for the kind introduction. So earlier in this conference, Matt Carlson came to me, and he told me that this was a system presentation. So I cannot have any video and any picture. So the only thing that you can have is code. And so that's what you're going to see today, a lot of code. This is essentially the outline of the talk. And so I'm going to start with some high-level motivation, and then afterwards we'll move on to low-level motivation. So we'll review the Objective-CP system in a nutshell, and then we'll do deep dive on a number of topics, models and concretization, search, and then the micro-kernel. And then we'll give you some experimental results and some conclusion. Now, why do we have high-level modeling and low-level modeling? Because, some of you are going to be completely unfamiliar with the syntax of Objective-C, so we want to give you all the ideas at the high level because they can be translated in any language which is reasonable. This is who is going to speak, so Laurent is going to do almost all the work. Okay, I'm going to just give the introduction, that's what I do these days. And I'll talk about something completely uninteresting, as Peter Stuckey has told you before. So this is the high-level motivation. Why do we do this? Because it's always the same when you build systems. We were completely frustrated with all the systems that we have built, and we wanted to try something completely new, a different balance between efficiency, flexibility, and what did I write? Simplicity. Okay, so we want to essentially find another point in this, space of systems and try to see, if this works or if this doesn't work. These are basically 3 things that we have done. Okay, so the first one is really viewing, an optimization program as the composition of 3 things. Okay, so models, a model, a solver, and then a search. Okay, now I have to give you the first disclaimer of this talk. So when we look at this point, we think, why didn't we do this, 15 years ago? It's so obvious that we should have done that a long time ago. But both Laurent and I are very slow, and we don't code very well, so that's what we have. We'll talk about search, and one of the big things that we want to do in search is basically telling you that with two very simple primitives, we can do everything. Okay, and so that will be the focus over there. And then we'll talk about the micro-kernel architecture of the CP solver as well, and how we can build CP solver in tiny, tiny, tiny little pieces. Okay, so that's what we want. That's what we want to try to do. Objective-C. Why do we use Objective-C? So Laurent will talk a lot about this, but the basic idea is that it fits very, very well with the goals that we have at a high level, because the language has a lot of features that are really nice, and it's also a very small language. You don't have to spend 30 years to actually read the manual like some of the languages these days. Okay, so these are the official motivations. Okay, of course there are some unofficial motivations. So whatever I told you now is a big lie. Okay, I love that show actually because differential diagnosis is like debugging. So I'm going to give you the real motivation of why we are doing this, right? And so in June, Laurent and I had a life-changing experience. I was visiting Laurent in Connecticut, and instead we realized that over the last many years, we had actually built a lot of systems, okay? And so these are all the systems that we have built. The one we built together are in the box over there. And to give you a sense, this is about between 1 million and 2 million lines of code. We don't count anymore. But we were there, like, we were there, sitting, together in a room. And then we realized that, we are actually doing this because it's fun. Okay, so we just like coding, okay? Computational thinking is overrated, coding is not. And especially we like coding together. And so at this point, this is really why we are building these things, okay? And the other things that we are really enjoying now is that we have many more people that are coding with us. We have Phil Kilby, we have Thibaut, we have Andreas, we have, Victor, Halton, and so on. And so these guys have plenty of new ideas, and they come to us and say, why don't you try this? This is ugly. Why don't you do this? And so this is essentially giving us a lot more ideas that we ever had, okay? So that's the real motivation why we are doing this. It's just because we have a lot of fun. Now, I want to do a number of disclaimers, okay? And the first disclaimer that I want to do, I don't want you guys to use Objective-CP, okay? So there are plenty of good solvers over there. Use them, okay? Don't come to us, asking for the system or asking for features or bug reports. No, we are just doing this for having fun, right? So please don't. The other things that I want to tell you is that why are we using Objective-C? Okay, the real reason is that we don't want you to use the system, right? The syntax is ugly. It's using dynamic dispatcher. It's amazingly slow. So please, don't even look at it. So you'll see. That's why I have to give this high-level motivation. The syntax is so ugly. You'll see. And then the final things that I want to say is that next year we really want to win a mini-zinc competition, but that's going to be the mini-zinc competition for the slowest solver and the most ugly solver. Okay? So this is essentially all the disclaimers that I wanted to do before we talk. Okay, so now let's go back to the design principle. That's the unofficial reason. So we want to essentially build this optimization program as a model, a solver, and a search. And I'm going to go to the various steps of why we are doing this. So at this point, I think the key things that we want is that all the models be first-class object. Okay, so no system has really, models as first-class object. We want to be able to manipulate these models. And these models have only abstract object. There is nothing in them, but you just start manipulating them. And so one of the things that we have at NICTA now with Monash is a big team just looking at model transformation. It's going to be one of the things where we can actually really push the frontiers. But we need to do that to have these abstract models and to be able to manipulate them and do things with them. And so modeling is a key challenge. The models that we have in CP express all the structure. We can do really clever things, even if at the end we are generating very low-level code. Okay? So the language that you will see for Objective-CP is going to be at least as expressive as all the modeling language that we know of, and that's what we want. And essentially, when you see something like Opal and something like Objective-CP, there is almost a one-to-one mapping between all the constructs. Okay? Even though we are in a low-level language. Okay? So this is, for instance, the steel mill slab models in a high-level language, but this is how we want to express it. We define a model, but that model now is a first-class object. We can do all kinds of things about it, and Laura will show you that. And then we define variables in the typical way. We can minimize an objective functions. We can add global constraints, or we can add, any kind of algebraic constraints. So this is a model, but what you have to understand here is there is nothing. Okay, so it's an empty shell. All these are abstract objects. They don't do anything. They are absolutely just something that we can start from. Okay? So the next thing that we have is that we want a concept, we capture a pair of model and solver, and we call that a program, okay? And that's essentially saying, I have a model, and I have a solver, and now I create another object that we create a program, okay? And that program can be anything. It can be a linear program, it can be an SMT program, it can be a nonlinear program, it can be a CP program, a MIP program, it can be anything, right? But it's basically the conjunction of a solver, an underlying solver, and then a model, okay? And then what we have inside these programs is what we call a concretization. This is essentially a function which is going to transform the model into solver object, and it also defines a mapping between the model and the solver object. And that function is explicit. Okay, so we have that function and we keep it inside the program. Okay, so this is one line of code here. You have this model, you create a program, now you can manipulate this program. And this is once again a first order object inside the system. Okay. So once we have that, so we can create a parallel program using the same model. We can create plenty of models at the same time, plenty of programs at the same time. We can create a CP program, a MIP program, a QP program, and we create them at the same time, and we can run them at the same time. We can do all kinds of things with them. Every one of these guys will have its own concretization function associated with it, which basically means that we can map the model object from the model into solver objects inside the solver. Okay? And so essentially these programs are already keeping these concretization functions, and they can do these mappings, when we do interesting things inside the solver, inside the search, for instance, and inside other things. So in a sense, this is a high-level view of what is happening in the systems. You have the model there. You could have the equivalent code in a CP program, and this function is saying, oh, but that variable, okay, which is a model variable, corresponds to these, concrete variables over there, okay? And that's what the concretization function does, okay? So if you have several of them, the concretization is going to basically say, oh, that model object for this program corresponds to that implementation. For that program, it corresponds to that implementation, okay? And so if I have to summarize what we have, these models are first-class objects. They are really empty shells. You have the variables, the constraint, the objective. Everything there is abstract. There is nothing in them. It's really lightweight. And then you have a concretization which basically map, okay, for every one of these concrete objects to a solver, and we keep that concretization so that we can make the link between these things, okay? The program encapsulates the solver, and it keeps the concretization function, and this is really important. The user will never see, never see the concrete object. They don't even know that they exist if you work at the, if you only use the system as a user, okay? And so this is very nice because you don't have to work with different concepts. You have only one concept of variables, that's your model variables, only one concept of constraint, that's your constraint, that your model constraint, okay? So this is an example. You take your CP program, you solve it, you get the solution pool, and then you can actually find the value in the solution of your particular model variable. So you can do that. You don't know, there is nothing in here which tells you that you have actually concrete variables behind the scene, okay? So the programs are always using model variables. The search is always going to use model variables, okay? Now, so Peter just sleep for a moment, okay? So the last component is the search, and in many of the applications that I've shown you yesterday during the talk, what we use is very specific search, okay? So it's very important for very large-scale complex applications. Why? Because we always use all kinds of hybridization, all kinds of materialistic decomposition techniques, and we can use all sorts of things like symmetry breaking, dominance relations, and so on. And so in a sense, we want inside the system the ability to program the search, and this is not a criticism of black box search. Both Laura and I are working on that topic as well, but we want both inside the system. We want, default search, but at the same time, we want people to be exploiting the capabilities of the system. And obviously, one particular, research area is going to feed into the other ones, and that's what we want inside the system. This is a system which is really built bottom up and which is really, compositional, as you'll see. So this is, for instance, the search, okay, and you'll see once again there will be one-to-one mapping into the real call of Objective-CP, okay, so you can solve this thing with this search procedure, okay, which basically iterate over all the variables, take the largest value which has been assigned to one of them, and then try the values for the next variables which has not been assigned yet, with, and this is doing some kind of dynamic symmetry breaking. The key interesting thing here is that all the search mechanism, like the trial and all the other things that I will show you, there are very few of them actually, are completely independent of the solver, the kind of programs that you are using. They can be used on top of a MIP solver, they can be used on top of a CP solver, of an SMT solver, anything. Okay, so you basically program your search here, and these things have nothing to do with the kind of programs that you have. They are completely independent. Okay, and you'll see the implementation is like that as well. Okay, so essentially all the search primitives are generic. They don't depend on any specificities of the solvers that you are using, okay? So if I put a parallel program there, it's going to work in exactly the same fashion, okay? Yes, obviously, what you can do inside this search is use the language feature to actually query the solver, add constraints to the solver, label the solver. You can also query the solver, the program, to get information of the variables. Once again, this is very natural, but this is completely orthogonal to the search feature of the language. Okay? So once again, you can query all these things, but they are not part of the search language. They are available because we are in a host language, essentially. Okay? And we can query the program. Okay, and once again, one of the important things that you see here is that we have absolutely no clue about what are the concrete variables which are basically used inside the solver. The search is entirely done at the modeling level. Okay, nothing here knows exactly what kind of solver we are using behind the scene. Okay, so this is the summary of the design. Models, first-class object, very important for us. We're going to keep manipulating these things, and Dan is going to give a talk later in the week to show what kinds of things that you can do as soon as you have a model as a first-class object. The model and the search are expressed only in terms of model variables. The users at the high level will never see the concrete variables. It's only if you want to extend the CP solver or the MIP solver or the SMT solver that you're going to actually see the concrete variables. The search is also independent of the solver, once again completely separated, and the concretization can actually do incredibly rich things like hybridization. We won't talk about that today, or parallelization, but you can do really interesting things behind the scene in the concretizations. Okay? So one of the things that I want to talk about is also the way the system is built. The system is built in a very compositional fashion, so we have this model that we start from, then we have these operators that I'm going to change the model and define them in models that are appropriate for a particular solver. You will have the concretization, okay? For the various program, and they're going to be, these things are, this is only the only place where you start being solver dependent, okay? And then essentially the key point here is that you want to define a new module, and we are very interested in routing at Nixa. If you want to do that, what you do is you just have to extend slightly the concretization functions which are there for the new concept that you are introducing for routing. And you can do that for the CP program, you can do that for the MIP version of it and everything like this, okay? So essentially what you'll see is that all the extensions here are going to use a concept that Laurent will talk about, which are categories, which basically means that you can extend everything without touching the code, without even recompiling the code. So that's actually pretty nice, and that's one of the features of Objective-CP. So when we look at the system extensibility, we have the core, we have the models there, we have all the concretization functions. One of the things that we are doing now is essentially building a new MIP, nonlinear MIP solver, nonlinear mathematical programming solver. You just need to put these concretization functions there and implement this guy. The rest of the system doesn't change, okay? You want to do routing, you put your routing extension there, so that's basically extending the modeling layer. You put a slight variety of these routing, you change these concretization functions slightly, and you get these various things. And you can do that for scheduling, that's what Andreas is doing right now. And obviously, in Nicta we are very interested in explanation, so you can change all these things there to have explanation solver for everything that we do. And once again, this is not going to affect anything of the rest of the system. It's just the solver there at the very end which is going to change. And so Thibaut and Andreas are doing things like that right now. Okay, so the search, so the things that we're going to present today is essentially two things. We're going to show you at the high level what the search looks like, and you're going to see search combinators which are basically inspired by and non-deterministic programs that are inspired by OPL and what Laurent Perron did in iLog Solver a long time ago. You're getting old, Laurent. And then we're basically going to show you that all these things can be built very compositionally using only two concepts that we introduced a long time ago as well. And so the big thing here is that you can actually reconstruct everything like this, and we'll show you essentially that in very, very tiny code you can actually do this, okay? And that's what we'll show you as well. Okay, so the last thing that we're going to talk about is the micro-kernel. So when I came to Nicta, we have an amazing operating systems group in Nicta. They basically build this micro-kernel operating system, and that micro-operating system is as efficient as the monolithic systems that people have built in the operating system community before. And so this was a big inspiration for us, and we said, okay, so can we actually build a constraint solver like that, where we have only tiny little piece, okay? So the core you'll see is a small propagation engine that doesn't even know that there are constraints or variables and things like this, and then the rest are going to be modules which are completely external to the engine. So we're going to say this is really cute, and so the system now when we build it, we just have to look at tiny little pieces when we want to do something about them. So this is the architecture essentially. You see the program will have an engine which is going to be solver specific, the search is going to be completely generic, it has nothing to do with the solver, and then we'll have the micro-kernel there and all the other extensions. If you want bit var or float var, they are completely separated, they don't touch anything else in the system. Okay? So that's the high-level motivation, so now I'm going to let Laurent do the rest of the work.
Thank you, Pascal. Okay, so from this point on, if we move on and we start looking at this, probably the first question is why Objective-C? So let's take another look at that. And what we believe is that it's a good trade-off. It's essentially C-based. It's Smalltalk. If you remember Smalltalk, yes, it's still alive in some languages, and Objective-C is one of them. And it's used by quite a few people, actually, and we don't necessarily realize that. It has very good language abstraction, and I'll touch on a couple of them to show how critical they are. And what it gave us is the ability to reach that balance between flexibility, simplicity, and efficiency. And I think we strike a good trade-off because of the language. So in terms of the reception that Objective-C has in the community in general, not just us, but all people using systems, it's fairly way up. And this index comes out every month. It's been stable, and Objective-C has been gaining traction. Of course, it changes from time to time. Every month you have a new ranking, so we don't need to take this for granted, but it's been rising in popularity over the last couple of years. It's completely compatible with everything that you write in C or C++. So you can write the propagators. If you want to extend the system, you can write them in C++ if you choose. There is a big user base, and it's easy to understand because of the iOS and the macOS ecosystems. The nice thing is that it has key language features to actually help us build things in a very elegant way. So, you know, C language, yes, it's compiled, it's efficient, completely compatible with C, right? It is C, but it has a runtime on top of it that gives you Smalltalk functionality. And that means, yes, terribly slow dynamic dispatching, complete introspection on the object, so we can actually examine the state of objects at runtime and modify things, add method on the fly if we have a need to. It has the popular type of things like classes, interface, and categories. There are referred to under funny names with a funny syntax, but they're really nice if you want to use them. And it supports loose typing if you decide to, but you actually can strongly type your program if you prefer to do that. One nice thing is the availability of first-order functions and closures, and they're called blocks in Objective-C, and they're extremely useful. So I'm going to focus on just these three pieces to explain why. Blocks, that's closures. If you're used to functional programming languages, you know exactly what I mean. Continuations, they're similar to what we introduced in Comet, and categories is really nice from an API standpoint for actually building things very easily. So, blocks. Same thing as in Smalltalk, you can turn any block that is anything that's between two curly braces into a first-order function. They can take arguments, they can return values, they're stack allocated, which means they're blindingly fast, and you can actually copy them and put them on the stack, on the heap to use them later on. Better yet, they're objects, and they behave in this fashion. You can send them messages very easily, so they integrate nicely. Here's an example, has nothing to do with CP. Imagine you have a set and you want to loop over it and do something with every element. You would enumerate the set and pass to the enumerator a block, a closure that basically here does something as silly as simply printing the actual entry of the set. So it's nice and it's very flexible. Continuations, that's the same idea as we had in Comet. They're built in Objective-C by us, so it's a small extension that we did. What they allow you to do is really control your execution flow. You can save it, you can restore it, and we created those with objects as well. So just like blocks, they are represented by objects. And they're really nice to build search combinators, and Pascal will come back to this later on. Categories, this is really nice as a programming language feature. It allows you to add method to existing classes, even if you do not have the source code. You retain very simple APIs. It allows you to actually inject things in superclass so that all the subclasses all of a sudden inherit from these new methods, and it's completely binary compatible. No source, and it's not a problem. And we use this quite extensively. Now, if we look at this, at the system in a nutshell, the way it's organized, the code, is in a number of frameworks. Think of those as libraries. What we have done at the bottom is that we're simply reusing the Coco or GNU Foundation classes for very simple things, and we're using Gurobi. But the rest above is written by us. So what we find foundations, that's where we have things like expressions, continuations, trailing, our arrays, our sets, all of this is in there. The modeling layers, that's where we put the models, the operators, the concretization, that's in this layer. The micro-kernel, of course, all the finite domain, reasoning over the integers, is separated into another framework. That's where we have the finite domain solver, the math programming library, and on top of it, the program is where we put everything that's very generic, like parallel support or the black box search facilities. If you wish to build a layer doing scheduling, it comes completely on top. Same thing for routing. And what happens is that these extra blocks, they show up as separate framework, but what they do is that they inject code in existing classes of these various frameworks through categories, so that they look completely natural, completely native. They are not special cases in the implementation. Now, looking a little closer, I start by looking at the concretization, at the models, but the first thing is, let's take a look at, from a user perspective, at what it looks like to write an Objective-C program. And for that, I, of course, will use the Queen's problem. I haven't seen it yet this time. So here's your typical C program. An auto-release pool is just for memory management, standard Objective-C. What I do here is create an integer for 8 queens, create a model. That's the first thing. They're explicit. We use a factory to obtain a model. Once we have that, we create a range. We create an array of integer variable whose size is driven by the range and the domain is given by the range. Once we have that, and notice that we give all of these guys belong to the model. Once we have this, we set up loops to start creating the naive formulation, say. So a bunch of binary disequalities, and that's how we do. We add the constraint, which is an algebraic expression. We add it to the model. We do, of course, the same thing on the 2 diagonals, and this is it. At this point, what we have is a model. Now, the model is, as Pascal said, an inert entity. It can't do anything. It's purely descriptive. You want to actually do any sort of solving, you need to create a program. And what you do is that you pass the model to this method to create a program for a specific solver. Now, what you get back is something that is executable, that has the ability to solve, and if you want to do that, you're going to actually say, fine, let's actually call a method on this, and just reminiscent of Comet, if you want to produce all the solution, you ask to the program, I want to solve and find everything, and what you give is a labeling procedure that's going to label all the variables in the array, and again, this is a method on the program itself. Notice here that if you want to start counting solutions, you back in traditional programming, so I just declare a variable number of solutions, I increase, and I print out my number of solutions at the end, nothing special. The whole thing here is relying on search combinator. This solve all message that you're sending to the program is a combinator, and we'll come back to these guys a little bit later on. What you pass to the combinator, and we do this extensively, is a block. It's a closure, it's a piece of code that will be executed by the combinator to do exactly what you want. Now, in terms of modeling, we have three ingredients, right? We have models, operators, and concretization, as Pascal described. So, what's in a model? That's the first question. Well, a model is essentially, think about it this way, a set of variables, objects, constraints, and possibly an objective function. Everything is lightweight, purely declarative, and supports introspection, so that you can actually do these model transformation. From the example we've looked at, the queens thing, of course the objects are the ranges, the variables, it's our array of queens. Constraint, the fact that the variables are discrete, that they have a domain, plus all the binary disequalities that were provided as algebraic expression. Everything belongs to the model, so that if you wish to have multiple models, no problem there. The model API in itself allows you to add entities inside the model or to inspect the content of the model by iterating over its content. Model operators, think of them as simple functions that operate over model. They take a model as input and produce a model as output, and they can do all sorts of very interesting things. Some of them being semantics preserving, like decomposition, reformulation, some being relaxations. They are changing the meaning of your program. They could be continuous relaxation, they could be linear relaxation, or anything that you can think of that makes sense. The requirement that we impose on this is that while you can add variables, you cannot drop any. You only growing the set of variables of the model as you keep applying these operators, which of course implies that we can do something very interesting with these guys. We can chain them. But first, if we look at an operator like flattening, imagine here you have a model full of algebraic expression. In reality, as we know in most solvers, there are mini constraints that take care of parts of the expression. What we do in the flattening process is replace all the algebraic by basic constraints, and we clean up the objective function as well. So imagine you have something that uses an element, it gets replaced by this system of basic constraint plus an auxiliary variable. That's the job of the flattening, that's what you get as a result. Original variable plus the auxiliary and the basic constraints rather than the expressions. These operators, as I said, you can do lots of interesting things, including composing them. That is, given a start model, if you apply the operators in sequence, you can get a series of transformation. What's important to see on that picture is that the last model in the sequence is still related to the original. I have kept all the relationship on the variables. If I add a variable in the model, I know its counterpart down there, down the line. And on top of it, we can fork. We can actually build trees out of this, and we can have models using, say, different relaxations to obtain different representation of the model or different reformulation. At the end, we have an entire tree, but all the leaves of the tree are still related to the original. We keep growing the set of variables is the only thing that we ask. Now, given this, we can apply concretization, because these models at the end of a sequence of transformation, they are still inert. You can't do anything with them. In order to solve, you have to put them in a solver. And that's the concretization operator, which of course is again a function, which given a model gives us a program. And the concretization function is suitable for various technologies. You have one function for, say, linear programming, one for constraint programming. So if we take our tree here, what we do is we have multiple solver technology. We're going to apply tree concretization to the leaves. We're getting back tree programs, and then we can start doing lots of interesting things with them, composing them. And that's the pointer to Dan's talk. That's quite relevant for tomorrow. The nice thing is that at the moment we have as concretization the tools for tree technologies, CP, LP, and IP, but what we're doing is building more, including scheduling, routing, and we're doing everything with explanations as well. At least they're doing it, NICTA. We'll also have a forthcoming brand new constraint-based local search concretization coming on top of this. Now, if we look inside the program and see what's in there, there are essentially two parts. An engine that's responsible for all the reasoning, and an explorer that's responsible for the search, but they're completely separate, they're independent. There is nothing in the search that refers to the solver or the variable, which means that these two can be varied independently. Just to give you a sense, if we look here at this concretization call, right, where we create the program given a model, and we take a closer look, if you wanted to solve this problem with a MIP, you just change one line and you get a MIP. And you can actually solve it that way. Notice that the create MIP, if your problem needs to be linearized, as a convenience, it will actually call that operator transformation on the model before actually concretizing it. So it works pretty well. What happens when you have such a line? Two things. We create a solver, and we basically flatten it, and we concretize with the technology specified in the name. What we get as a result with the program is an auxiliary data structure, which is this concretization map that gives for every modeling entity the corresponding implementation entity so that it can be used. And you ask probably where, we'll see that in a moment, it's inside the search. In a nutshell, pseudocode going real fast on this, if you create a program, what's really happening is we're flattening, we're concretizing, and then we're setting up stuff for finding solution. That's not important. The concretization is here, it's using the introspection API, building a gamma map, that's the mapping between abstract model and abstract entities and concrete counterparts. That's basically going to concretize all the variables, all the objects, all the constraints, and remember that mapping gamma so that we can use it later on. Gamma, where do you use it? Inside the search. That's the typical place. So here, if I zoom in on what we're doing inside, say, a method called on the program to label an array, what happens is really something like this. The label array basically says we're going to loop over all the variable in the array, use gamma, which is inside the solver, so the user never sees it, right? This is the implementation of a method that's inside the solver. We use gamma to retrieve the concrete variable, and we actually do the branching on that. So that's completely hidden, and that's really nice inside the solver. The bottom line is that this is just one example of such a method on the solver, but as you've seen on Pascal's example earlier, we do this for everything, for querying the min, the max, the domain size, all the operations go through the solver to retrieve the actual value of a variable. Everything you do at a high level is in terms of the model. And that's the really nice thing, because it gives us the opportunity to do things like population-based algorithm or parallel computation without any trouble. We can do work stealing, we can do all of these things, all these very dynamic procedures, because we have this nice separation between the two. Now, we have to talk about search, but you know, we learned something very important 2 days ago, and search is dead, right? Now, I don't want to scare anybody, but if you know that search is a formidable foe, you might be thinking, well, alive it's a terrible foe, what happens when it's dead? And you might be thinking, we're in for some trouble. Thankfully, we have with us today one of the expert killers on zombies and search zombies in particular, so I'll turn it over to Pascal to actually save the day.
Oops. So thank you, Laurent. This is amazing because this is the first time I can give a talk and read email at the same time. But anyway. So I'm going to talk about the search design of Objective-CP, and essentially I'm going to focus only on one part, which is how we can build complicated search, okay? But obviously, you know, Laurent and I have been working for a while now on black box search, but we won't talk about that today. So the contribution that you're going to see here is that there will be a full blending of the search primitive of the language with the host language. So you basically write in Objective-C, and then you can interleave some operations, some search operation very naturally, and you'll see that in a moment, okay? It's fully compositional. One of the interesting things from an implementation standpoint is that the search is fully compiled, so there is no need for interpreting any kind of, you know, abstract tree or language or anything, or to rewrite that using mixin and so on. So this is pure Objective-C code which is compiled, and you'll see that the system in a sense is very, very tiny. So the search implementation is actually amazingly small, and you'll see many part of it today. And then it's technology independent. So one of the things that happened, you know, last year when I was discussing with Peter and Thibaut and Andreas never says anything initially, but anyway. So what is happening is that you know, Thibaut was asking, okay, so can we do, you know, a lazy close generation solver with an arbitrary search? How much will you have to change inside the system to do that? And essentially what you're going to see is that the language that we have can do that essentially automatically. There are a couple of lines that we have to add for adding new functionalities that you typically have in SMT or you know, lazy close generation solver, but the rest is essentially unchanged in the system. It's only if you add functionalities that we have to change something. So I'll show you some of these things later on. So the basic idea is that for us, the high-level search is a non-deterministic program telling you what the search tree is, okay? And that's a lot of the work that we did in OPL. And then an exploration strategy, which uses essentially search combinators, you know, like Laurent has done, and like, you know, people at Leuven and also with Peter have done recently as well. So literally a very simple labeling strategy here in Objective-CP, okay? And the key point that I want to focus on here is that this is purely Objective-CP code, except that you have a method call here for a non-deterministic construct, okay? So what you do here, you iterate over some int, you test the variable xi, which is a model variable, is bound or not, you know? If it's not bound, you take this minimum value, and then you try to label it with the minimum value, or if that doesn't, you know, on failure of this, you will try to label it with, so the other choice point is simply saying that the variable is different from that value. So essentially this is interleaving completely Objective-C code, okay, with the search primitive which is there, okay? So that's one of the things that you have to do. Okay? Now the key points here, and I want to focus that, you know, the system here, the search language, the try method has absolutely no clue what this is. It's a closure. So it doesn't know anything with any of the inside of this thing. It just knows that, oh, I have to execute that closure. And if I come back on backtracking or with another search strategy, I'm going to execute the other closures. So the search language only sees closures, nothing else. Okay, so this, of course, you can embed that in a function. This is exactly the same in a function, which basically means that all these things can be inside. They can be inside method. They can be interleaved in any part of the language. You write C code and you interleave some non-deterministic construct in there. Of course, you can do that recursively. I have no idea why you want that, but Laurent wanted to have this slide, so you know I concede it. But essentially, this is the same thing as you have said, except that it's recursive. But once again, you know, you have a try instruction here, which is basically labeling that variable. and then you call the method recursively, and it's going to work fine. Okay, so you basically can write any code, recursive, iterative, or anything, and interleave this with this non-deterministic construct. Okay, so in a sense, basically all the combinators that I'm going to show you, they are blending with the language in a completely symbiotic way, and that's what we actually that we like a lot. Okay, so now the limit combinators. So this is some of the pioneering work that Laurent Perron has done. Okay, and so these also are basically implemented inside the system, and I will show you how big or small the implementation of these things are later on. But at a high level, what you basically can say is that, oh, I want to limit the number of solutions to k in this particular closure. Okay, so you run this closure, it's going to search for things, but you only want that closure to succeed k time. Okay, so once again, this limit combinator, it can be used, on any kind of solvers. The only thing that it has, that it's manipulating are closures. Okay, and so you can nest these guys arbitrarily, in an arbitrary fashion. So you can say, oh, I want to limit the failure to 200 and execute this closure, and that closure has a limit on the number of solutions, and then it has a search procedure. You can embed these things in completely, you can interleave these things in completely arbitrary ways. There are no restrictions. The only thing they manipulate are closures, essentially. Okay, so this is the most beautiful thing ever. So I was completely frustrated in Comet because large neighborhood search was essentially a primitive of the language, and there is no reason for that. So what I'm going to show you is one combinator which can implement large neighborhood search in 3 lines. Okay, so essentially we have this repeat combinator, which is essentially taking a closure and executing that closure until it succeeds. Okay, and so what you see here is you have an example of the repeat construct. Okay, so it's basically going to execute this thing until it succeeds. Okay, and this thing is what is basically limiting the number of failures to some value here and executing this sort of closure. So essentially what you're trying to do is make this thing succeed. Okay, so if it fails, for instance, because you encountered the limit on the number of failures, you're going to execute this thing and try again. Okay, which basically means that obviously this thing has to be non-deterministic or something, or you can actually essentially. And so what you do here is essentially you try something, if it doesn't work you execute this, and then you retry and you keep doing this until you succeed. Okay? If you fail, obviously you're going to go back to an earlier state in your search. Okay? And so this procedure here, in a sense, inside the closure, this thing is dying, so it is essentially using activities, and Peter, it can be yours, it can be ours, it doesn't matter, right? It has to be randomized. Okay? So this is essentially, once you have this combinator, doing large neighborhood search is amazingly easy. This is all you need to do. Okay, so this is a large neighborhood search that Philippe Ruffalo proposed for the steel mill Slab a couple of years ago. And what you see there is that you want to solve the CP program. Okay, and what you're going to do is that you're going to limit, that execution for some amount of time, and then you're going to do this, essentially this large neighborhood search. Okay, and what it does is basically using this. Okay, and if you fail on this, you're going to execute the code which is at the bottom. Okay, I'm going to go into this in detail. Okay, do you see the colors there? Oops. So this is essentially the neighborhood search. Inside this is essentially what you do. This is what you repeat. If you fail, you execute the stuff at the bottom. What you do there is basically a particular execution of the search. You limit the failure to a certain limit, and then you execute this thing that I've shown you before. Okay? So the inside of this is essentially the search procedure for the steel mill Slab. Okay? So if you fail, in that particular search, you go here. What you do is you take the best solution so far, and then you enumerate all the variables, and with a certain probability you keep them to their values or not. That's what Philippe Ruffalo had actually proposed for this thing. So what is interesting here is that essentially large neighborhood search is just essentially embedding a search and what to do, on repeat when you fail using these repeat combinators. Okay, so that's the search that I've shown you before. Okay, and that's the non-deterministic construct that you have there, and this is what you do when you are actually failing inside the main body of the search. So essentially at this point, there is no need to actually have large neighborhood search as a primitive of your system. You can build it essentially using one combinator, a search procedure over there, and what to do on restart. And essentially what this gives you is an ability to basically build a combinator for large neighborhood search. We will take, again, 2 closures, and would be essentially an implementation which would take 3 lines. Okay? So these combinators are fully compositional, they can be interleaved in an arbitrary way, and they only work on closures. Okay? So now I want to talk about how you build these things. Okay? So I'm going to show you that you need only two key concepts, continuation and search controller, and all the combinators that I've shown you can be built using, a couple of hundred lines of code, even less. Okay? So, and these combinators are implemented bottom up. Okay? So I'm going to show you the 2 things that we need. We need continuation. Laurent has talked about that before. So what is a continuation? A continuation is something that saves the state of the machine, the stack, all the registers and things like that. And the control flow, what is the next instruction? It can restore the state even if the stack is smaller or larger, and then you execute the next instruction. Okay, so this is the API of the continuation inside Objective-CP. So you can call the continuation, you can find the number of times you've already called that continuation, and obviously you have a class method to take the continuation. That's all you need. Okay? This is the try instruction that I've shown you before, implemented with continuation. Okay? So what you do is essentially you take a continuation. If you haven't called it, you execute the left, otherwise you execute the right. That's the only thing that you need to do. It's very, very simple to implement the try combinators while you have continuation. Okay? So the controllers instead are not going to talk about the non-deterministic program. They are going to talk about the way you manipulate these nodes. If you do depth first search, or if you do something else, if you do limits, or if you do repeat combinators and things like that. And so a key point here is that these guys are going to be completely compositional to chaining, and therefore that's the way you can actually interleave them easily and have complete compositionality on that stage. Okay? So this is the API of the controller. Essentially what they do, they have various things. You can add the choice, and the choice are basically continuation. They can fail, they can succeed. For the trust, for those of you who still know about the Warren abstract machine, this is one instruction that tells you this is the last choice point of a particular choice. And then the rest is essentially instrumenting the various combinators, that with the various non-deterministic combinators, and I'll show you that in a moment, okay, to essentially let the controllers decide what to do at various points. Okay? So this is the try instruction. When you instrument it with the controller instruction, you basically said, I'm going to try, I'm going to start a try, then basically you say I'm trying left, I'm finishing left, and same thing for the right. Okay? So once again, it's simply telling the controller what we are doing inside the try instruction. Okay? So once you do that, so that's the control. So one of the big thing here that you have to see is that, well, no, that I told you that already. Okay, so essentially, if you have a DFS controller, the only thing that you have to do is manipulate, the state of the system and the continuation. On backtracking, you call the continuation. When you add a choice, you put something on the stack. So very simple to do. Okay, and so this is essentially a couple of lines if you want to implement that. If you want to implement a best first search controller, you will maintain a priority queue or something like this. Okay, so the combinators are basically built with these 2 things, and I'm going to show you how. Okay, so this is, for instance, the implementation of limiting the number of solutions. Once again, it's going to be a tiny little piece of code. The only thing that you do is you create a controller for limiting the number of solutions. You push that controller. This is really important because this is how you can chain them arbitrarily, nest them arbitrarily, and then you execute the body. You basically tell the controller that you have succeeded, and then you pop the controller and continue. Okay, if you exit that controller, you just pop it from the chain of controllers. Okay, that's all you need to do. You of course have to implement the limit controller, and this is the code of the limit controller. And what it does essentially is, when it succeeds, increase the solution to 1. When you are basically starting a try left instruction, you will try to see if you have reached the limit, in which case you fail. Otherwise, you delegate that instruction to the chain of the controllers. Okay, so once again, you want to implement a limit. This is what you have to write. This is the other thing that you have to write. Almost nothing. Okay? So chaining, so that's what I told you. These combinators are basically chained. If you have several of these combinators, so the solver, the program will have the controller, it will have the limit on the fail, the limit on the solve, and the DFS. Okay, so the code go there. If it fails, obviously it's going to fail. Otherwise, you go to this guy. Do you fail? No. Okay, so you continue, and then you're going to go to the final controller, which is going to do its thing. So you basically nest them arbitrarily in this chain to actually have full compositionality of the combinators. Okay, This is the repeat implementation. I told you that this was, really simple to do. Okay, so the only thing that we do, we take a continuation, we add a choice, with that continuation on the stack of choice points, and then if this is the first time, this is not the first, and then we execute the body. If it's not the first time you are calling this continuation, that basically means that you are actually repeating the execution. You execute the on repeat. That's basically, for instance, implement the part of a large node search where you fix some of the variables, and then you execute the body again. And so this is essentially the only thing that you have to do to implement that combinator, and now you have large node search for free. Okay? So you can also do full transparent parallel tree search, and this is one of the things which is really beautiful. The things that I've shown you before is that instead of concretizing with a CP program, you can concretize to a parallel program, and the only thing that's going to change is that the concretization function, instead of creating one solver, CP solver for instance, is going to create a bunch of them, and then the rest is done with the search controllers. And the search controllers are going to basically have something which knows how to actually do, let's say, that first search, but also generate nodes if other workers are starving. Okay, so this is essentially extremely simple again. So it's fully transparent in the sense that you don't have to change any lines of your code to actually move from a sequential program to a fully parallel program. Okay. So in summary, benefits, you can write arbitrarily C code and objective C code and interleave it with the abstractions that we have. At the high level, we write non-deterministic program. You can also implement, the search exploration strategy using these combinators. It's completely extensible. If you find tomorrow a new combinators, you can use controllers and continuations to build them. We haven't seen any that we could not build so far using these primitives. It's fully compositional because essentially we only use closures and we chain these controllers. It's fully compiled. Okay, so the code is compiled. It's compiled by Objective-C. And one of the benefits that we love is essentially when you debug, you see everything. It's basically you see your stack, you see the variables everywhere, you can move up and so on. You see exactly the state of where you are. There is no magic. It's purely compiled code of Objective-C. Okay, so this is the search part, and I'll give Laurent the floor for finishing the talk.
Thanks. Okay, so now let's take a look at the solver. I'll do my best to use the little bit of time that we have left. So Pascal covered the Explorer side, so let's take a look at the engine. And the main thing that I want you to see from the get-go is that we want to have something that's really minimal, support completely modern technique for building your propagator, and remain completely extensible. So the main thing is, if we look at that box, is that there are very few concepts inside the engine itself. There is the ability to load a model, and there is the ability to propagate. That's about it. Everything else is actually outside your domain, your variable representation, your constraints. There is your propagators. Whether they're on integer, bit, or float variables, they're completely outside. They have nothing to do with the kernel per se. The only concession is a very simple protocol, an API for constraints. We need to be able to name them and to post them. These are the only two things that we want to be able to do. Naming and posting, and we're going to take a look at how that works. And to do that, I'll use a very simple example that everybody knows, is a simple equality constraints propagator. So here's the equal on domain consistency. All it remembers are two variables in a constant. It's capturing x equal y plus c. And there is a post method. That's it for the spec. And here's the entire code. That's the whole thing. All you do is the usual thing, right? If a variable is bound, you bind the other one. Fine. Otherwise, you narrow the bounds. You punch holes as necessary. And you finally get to the interesting part where you're telling variable x that, hey, x, whenever you lose a value, call that closure. Once again, it's a closure that controls everything. And here it's even a closure with an argument. So it's a first order function that will echo the loss on x on variable y. That's all you need to do. The point is that these when lose are really the registration events on a variable. But remember that the variable is outside. These are closures, right? That's the main message is so far you've seen only closure. That's the only thing that really matters at this point. You look at an old diff constraint from Jean-Charles, for example, it's the same kind of a story. We're going to have different registration. Here, whenever a variable gets bound, here we're registering the fact that when any change happens to the domain of a variable, I also want to execute a specific function. Here, the propagate function of the class, and here what happens is we have the logic for the propagation. It's completely separated in this fashion. What's in a variable? Essentially the domain representation, it's your choice, and the list of responders, that is who should be notified, which closures should run when something happens. And you're in control of defining that when you're defining your variable. I'm not talking about triggers, watch literals, but they're in there as well, we can do that. What really matters is that when you're defining a variable, what you do is give the engine that owns the variable, the domain. Notice that the domain is completely separate. It's an object, so it can be polymorphic, list of interval, bit vectors, whatever, you name it. And then we have the responders. These are basically a list of people responsible for responding to notifications of events. Here what we have is the registration capabilities, where we are hooking up first-order functions or closures to various kinds of events that we have defined here in those lists. Finally, the API to make the change on the variable. Change the min, punch a hole, that sort of stuff. Now, if we look at this, essentially the implementation of the APIs for registering are simply adding these closures inside the list. That's all there is. And if we want to support priorities, we do. That's the same thing when we are putting entries inside the list. We are actually pairing them with priorities. So these, a queue like min, for example, is just a list of closures plus priorities for them. Now, if we look at what happens when we touch the variable, that is, for example, updating the min, we do the operation on the domain. If that results in an actual change, we grab the list and we schedule it on the engine. So that's the only time where the microkernel actually sees anything. He sees the list of closures that needs to be scheduled, and he will be responsible for dispatching them. That's the extent of it. Of course, we notice that if the domain is becoming of size 1, it's the variable is bound, we have to schedule, for example, the bind queue of the variable. Okay, so this schedule corresponds to putting all those closures into the right propagation queue driven by the priority, and that's all there is to it. So the main thing to remember, what is there really inside the microkernel, only one thing, events. That's the only concept, and these events are basically responsible for their being scheduled and propagated by the kernel. That's the only thing that the kernel has to worry about. So we have methods here for doing the scheduling, and we have the same thing for the triggers, the watch literals, and then doing the entire propagation. That's the extent of it. Now if we look at the entire propagation, or the events in particular, it's only closures, right? That's the one thing I want you to remember, is that they can take an argument if there is a value associated with the event, and all the kernel has to do is dispatch those closures whenever the event has been scheduled by the variable. So the variable does the scheduling, the kernel executes it. Inside the kernel, the propagation, right now what we have is just a collection of priorities, and its only task is to propagate. The code is actually very short. This is all we have, the ability to actually pump all the queues that are in the system. Here the try-fail is to basically say if a constraint reports a failure or a variable reports a wipeout, we want to catch that and divert the execution to this handling of failures. Otherwise, here we're pumping the queues in descending order of priority. Nothing really fancy. There is a special Q0, which we always do, which is kind of nice. Even if you have a failure, events that you want to always execute end up in Q0, and that's what you want to do at that point in time. So the Q0 is done in both cases, whether you succeed or whether you fail. If I just take a minute or so to actually go over some results to give you a sense of how well this works, because it's fairly generic and it's really meant to work on small pieces at a time, and we heavily rely on closures. So how good or how bad is this, right? Here what we did is basically see the cost of separating our model. The fact that we have a model that we're going to manipulate, decompose, and then concretize. What you see here is the running time in milliseconds, average and standard deviation for a bunch of benchmarks, and what you see there in the last column is the time it takes to manipulate the model, the flattening step, the concretization step. This is the part that's separated. You see that time in milliseconds as well. Of course, this is much smaller than the runtime that we have on this side, so the cost is really inconsequential. We shouldn't worry about that. Having our model fully separated is not a big deal. It carries very little cost. What you see here is how much bigger the model gets as a result, the expansion, the growth. As we are doing the decomposition, you might introduce auxiliary variable. Think if you have verification or whatnot, you have how much bigger the model gets as a result. We compared to Comet on a number of problems, including perfect squares, port scheduling, Slab, to actually see the behavior. Again, times are in milliseconds. The basic message here is that it's doing fairly well compared to Comet in terms of performance. But of course, you know, not everybody might actually remember how well Comet ran or how badly it ran. So we thought, hey, maybe this week we decided, oh, let's add a little comparison to a solver that people know in the community and can relate to. So we did a comparison with Choco, and that was just done this week to just give a sense of how well it behaves. Just a collection of benchmarks, getting all the solutions, just made sure that the number of the search heuristics were the same, the number of solutions was identical in these problems, and here of course for the magic square, different sizes, but we used IBS and we simply reuse all the benchmarks as they came shipped with the library. So this is the behavior of Choco. What you see here for the memory footprint is the resident set in memory for the entire system, and these are the runtime. Now, despite dynamic dispatch, we're not too displeased with the result. We're doing fairly okay. I think that the price is perfectly reasonable for the system at this stage. Now, last thing I want to show, yes, we have black box search in there. The fact that we have open does not prevent us from actually building these generic searches. And we tried a number of things like impact-based search or activity-based search. I know Peter doesn't like the name, but here it is, it's still there. What we see is that the results are really comparable and often exceeding a little bit what we were getting with Comet. So this is fairly reasonable too. So bottom line, let me finish by saying that Objective-CP is all about models, and the fact that they became first-class citizen, we can completely separate them, we can do transformation on them, we can concretize, we can have multiple programs that we can hybridize in very interesting ways. The search is very powerful with combinators and a complete seamless integration in the host language, which makes life much easier, and we're relying on the micro-kernel for the finite-domain solver, which is a perfectly valid way to go forward for having systems that are easily extensible. Writing new propagator or new domain representation or new variable type is fairly easy. So we believe that we are striking a reasonable trade-off between our three objectives. So with this, I close the talk and we'll be happy to take any questions you have. Thank you. Yeah? Good.
But I seem to me that you don't want a separate modeling language now, and you want the model and the host and the solver. So the model in the host language and the solver is kind of in the same host language and so forth. Is that the main?
The main thing is completely, we are trying to really separate the model so that you can actually do all sorts of things and refactor and have all sorts of model transformation that are reusable regardless of which technology you end up using underneath. The benefit is, for example, you are capable of creating a model and using different technologies, a MIP, a CP model, a constraint-based local search, and hybridize them, either with parallel search, with sequentialization, with sharing of bounds. You can easily do that, but you don't have to remodel your problem multiple times. You actually have a single model out there, and everything that you express afterwards is in terms of that very high-level model. So it's a big flexibility. The search that we get is, we still believe, even though the search is dead, we still believe it's a hard problem, and we need it on the big problems that are out there. And the ability to write search in a very elegant way and have it completely independent of the fact. Remember, the search is not for finite domain alone. It will work with any kind of solver, which means if you want to start doing sophisticated sophisticated things with a MIP, sophisticated search, which are semantics driven, you can actually do so. So that's what we wanted to achieve. It's really this nice compositionality. It's a great platform, at least in my opinion, for doing research, as it separates all the concepts and allow you to compose them very effectively.
No question?
So systems like Numberjack, Essence, and Zinc have sort of separated the modeling phase. So these programs all do modeling, and then when they've created a model, they give it off to a completely separate solver, often usually written by a different group of people entirely. So what benefits do you think you have that you're doing the modeling and the solving in one tool as opposed to separating it into two independent programs?
Here, the fact that they're inside the same platform will allow us, when you get these programs that you can run concurrently, they can exchange information. You do everything in core because you have all the representation present and available for actually doing this sophisticated form of exchange, because everything that you do and that you pass around, including solutions coming from, say, one program, you can feed them into another because they are expressed at the modeling level. And because everything is in the same environment, it's much easier to do so. So Pascal has something
so there are other things that I think are very important. So one of the things that we build also is the CP solver is just a core technology that we have, but we always build a lot of things on top of it, like scheduling, like routing, like a non-linear solver on top of it. So when you do things like that, it's actually you extend the modeling language. So you don't want to be stuck with extending various systems. So here you have one framework where you can extend the modeling language, you can extend the solver, you can extend the concretization, you can extend the solver in a compositional manner. So that's a big advantage if you want to do things like that, if you want to build things bottom up like that. It doesn't prevent us from using a modeling language, right? So the modeling language can be the input of an objective CP program as well, okay? So you have, in a sense, the flexibility of using a modeling language, but you also the flexibility of actually adding modeling layers and adding, solver capabilities inside the same systems. And I think that's also very nice. And then the last thing is that most of the modeling language will typically they will have to lose efficiency typically when they do search, when they do very specific things. And so in this particular case, you don't have to do that. You don't have to lose that. You are really compiled. You are inside a low-level language when you run the stuff at the end. Does that answer the question?
Yes.
Yeah.
So I would suggest to continue the discussion.
The coffee break? Last question here?
Last question.
Okay.
So my question has to do with the target audience for the system. It seems like it's a system for experts. You mentioned closures to your average person who has an undergraduate degree and their eyes glaze over. But those people, maybe we want to get the CP technology to such people. In other words, won't have CP people, experts, developing all of these solver or applications. So how do you see that part of it would work with your system?
So I think it's a great question, Fahim. Thank you for asking. I think, once again, when we started motivating the system is that, you have a large space of things that you can do in this community, right? So you can focus on modeling, and this is something that we had done before, and it's successful for a particular class of audience. And so what we wanted to do here is something which is very different. It's having a system which is as compositional as possible, and it's true. I mean, you have to be an expert you have to be a programming expert to actually use the system, but then you can build these layers that afterwards will be available for building specific blocks. So one of the things that, for instance, we are doing in NICTA is also building things like, power system tools these days, right? And so you need a system like this these days to actually build these things, because they don't have the maturity of some of the other applications that we have. They don't have the maturity, let's say, of timetabling or scheduling at this point. And therefore, when you do this, you want to have a flexible language to try actually how you solve these problems and how you actually build them. But then you can abstract all this into a power system tool where the only thing that people are giving you is a power system model, and that's it. We want to have this kind of flexibility below, such that we can go to the next step, which is building this kind of dedicated solver for particular application areas. So yes, you have to be an expert, and that's part of the targeted audience here. We want to have something which is really flexible, but also easy to use in a sense, easy to extend, because most of the systems that we have been familiar with are very difficult to extend in general. You have to build a system to actually be able to modify it in a sense, easily.
There is also the fact that closures are not all that crazy anymore. If you look at all the programming languages that are extending to add, they come under different names, right? Anonymous classes, lambdas, they're appearing and popping everywhere. Programmers are getting used to building user interface using this because it's very convenient.
So let's thank again Pascal and Laurent.